Hey everyone, if you're joining us to talk about ternary ionic compounds, we are going to do that in a moment. So we are going on a journey over on this branch, highlighted in purple, of our flowchart. You'll notice that we are going to deal with things that have a polyatomic ion in them. But before we do that, I want to back up a little bit and chat with a periodic table about just when it is we need to worry about cations that can have more than one charge. So first off, you'll notice that I've drawn the metalloid staircase here, and over here to the right of that staircase, we have ourselves the non-metals. And the non-metals always have a known charge. So if you remember, we said that this column over here, the noble gases really won't bond, but if these guys form ions, they'll always be -1. If these ones form ions, they'll always be -2. If these ones form ions, -3. We won't really deal with this column either because they can be plus or minus. That's what makes carbon so useful. That's why it's like kind of the backbone of all living things in organic chemistry. But for us, we're really worried about those -1s, -2s, and -3s. Similarly, on the right-hand side, we know that the first column is going to be +1. The second column is going to be +2. And as a reminder, we can predict why that is, right? So we know that if we look at the S sublevel, the first column is going to have 1 valence electron. So how many does it want to get rid of to get back down to a full valence shell? Well, it wants to get rid of 1. That's why it's +1. The second column has 2 valence electrons. How many does it want to get rid of to get down to the next valence shell? It wants to get rid of 2. That's why it's +2, right? So there's logic behind the ions that they're making. And very similar over here, if I look at my nonmetals, if I drew in my electron configuration, we're in the P sublevel, right? So here's the P sublevel. Things in nitrogen's column look like this. They end with P3, right? So they have 3 vacancies. That's why they want to gain 3 electrons. Things in oxygen's column look like this. They have 2 vacancies. That's why they want to gain 2 electrons. And things in fluorine's column look like this. They have 1 vacancy. They want to gain 1 electron. So again, there's logic here as to why these things form the ions that they do. But it turns out we have this huge area in the middle where we don't really know what metal, what its charge is going to be. And so I'm going to outline a box here. And it's pretty simple, right? It's this entire box all the way over to the staircase, like so, and this entire box. And it turns out if you have a cation in any of that area, it can have more than one charge. And so you need to therefore give it a Roman numeral or a classical Latin name. Now on your resources for the whole year tab, we've given you some of the Latin names that are really important for you to know, right? So we've given you, honestly, the atoms that have the most common Latin names, and you'll see them there in the classical column on the left. We've also given you their name with a Roman numeral. So if you encounter an atom that is here in the middle of this green box, and we've given you its classical name, you need to be prepared to give us both the classical or Latin name and the Roman numeral. So for instance, we gave you iron. You need to be able to tell us about ferric and ferrous, and also iron 2 and iron 3, right? So you know that iron 2 is ferrous and iron 3 is ferric. But what if we gave you something like manganese, right? Manganese is not on your resources for the whole year page. That means that you should be prepared to name manganese with a Roman numeral. It's in the green box. It requires a Roman numeral, but you don't have to worry about the classical name because it's not one of the ones that we've given you to know. Again, we've given you the ones that are most common. Now there's one final amendment to this. I've told you that everything in the green box requires a Roman numeral. That is relatively true with a few exceptions. Now, fortunately, the exceptions are written right here. So these 5 elements happen to be in the green box that we see on our periodic table. However, they always only have 1 charge, just like these cations that only ever have 1 charge. Cations that always have the same charge do not get a Roman numeral. In fact, it's incorrect if you give them a Roman numeral. So for instance, if we look at sodium, sodium is always a +1. We do not write sodium Roman numeral 1, ever. We never do that, right? Why do we not do that? Because it's always a Roman numeral 1. So we don't put that Roman numeral with it. It's just sodium. Whereas something in the green box requires a Roman numeral, with now the exception of those 5. So those 5 are aluminum. Let me write these in purple. Aluminum is always a +3. Always, always, always. Zinc is always a +2. Silver is always a +1. So you'll notice we have a little staircase going there, 1, 2, 3. And cadmium is in the same column as zinc, so it's also always a +2. So those 4 aren't bad. And then finally, the last one to be aware of that always has a single charge is scandium. So over here, scandium is always a +3. Now we're giving you that resources for the whole year page, right? You have those 5 to be aware of, and you have them in front of you. You know what charges they're going to be. But you just need to be aware of them as you start to think about everything in these green boxes requiring a Roman numeral. Notice that those 5 elements never get a Roman numeral either. So for instance, aluminum is always a +3. We simply write this as aluminum, not aluminum 3. This is incorrect. Even though it's a +3 charge, it's always a +3 charge, so we do not require a Roman numeral. So we'll keep using those as we continue to practice, and let's do that by practicing some ternary ionic compounds. Now, ternary means that we're going to have a polyatomic ion. So here is your list of polyatomic ions. Poly meaning many, atomic meaning atoms. So these are ions, but the entire ion, for instance, carbonate here, the entire CO3 group of atoms has 1 charge and it's -2. So polyatomic ions are ions, but they're ions that exist as a group of atoms. So you'll want to have this out, you'll want to have your periodic table out as we step into naming ternary ionic compounds. So let's talk about these polyatomic ions first. The polyatomic ion piece of this is bound together through covalent bonds, and I know we're talking about ionic naming right now, but the polyatomic ion itself has this covalent bond that holds it together, and that means we can treat this as a single group of atoms. It's a single entity, and so we give it a single name. So for instance, SO4-2 is always just sulfate. And so when we're thinking about our anion, we said the anion is always something where we know its name. It's never going to have more than one name, and it's also always going to have a given charge. And that's true of polyatomic ions as well. So let's dive in, and let's dive in again on the right-hand side first. So we're going to try name to formula first. And just like always, we are going to write out the formulas first. So carbonate, if you look it up on your list, carbonate is CO3 with a -2 charge. And sodium is Na with a +1 charge. Right? And you could think about how many sodiums and how many carbonates you need to cancel out one another. A lot of people like this crisscross method, and when they crisscross this thing, they say, okay, well the Na is going to have a 2 next to it, that's all well and good, and then the carbonate CO3 is going to have a 1 next to it, that's all well and good. That's not all well and good. You have not done this correctly, right? What you have said here is that you have 2 sodiums, cool, you have 1 carbon, and you have 31 oxygens. 31, that is not good, not good, not good, right? So that's a problem. So we have to be aware with polyatomic ions what we're doing, and sometimes we'll need parentheses as we'll see in a second. But remember that this 1, when you cross it down, disappears. So really what we want is 2 sodium ions, and we want 1 CO3 group. We don't want 31 oxygens, we want 1 CO3, and so we leave it like that. Look at number 7, calcium nitrate. Calcium is Ca+2. Nitrate, you can look up on your list, is NO3-1. So now we have an issue, right? Because when we cross these charges or we think about how many we need, I just kind of yelled at you on the last one for having 31 oxygens, but look at what we have here. There's going to be 1 calcium, and then we have NO3, but there's a 2 that comes down with it. So you're like, what the heck? It kind of has to look like NO32, right? Like 32 oxygens. So there's a trick that we use, which is that this NO3 is a single entity. So to keep it as a single entity, we want ultimately 2 of that single entity. So what do? We are going to put it in parentheses. And this notation, the way we read this, states that we have 1 calcium, right? There's 1 of those, and we have 2 NO3 groups. Now, if we asked you to actually count up how many of each atom, you'd say, well, there's 1 calcium, and then you distribute the 2. So there are 2 nitrogens here, and there are 6 oxygens. But we don't write it out that way because this isn't a covalent compound, it's an ionic compound. So we use the parentheses, but just recognize that that 2 does distribute to everything inside. Let's talk about plumbous chlorate. Again, your resources for the whole year is going to be really helpful to you here. So plumbous is Pb with a +2 charge. And chlorate is a polyatomic ion that you can see on your list. It is ClO3 with a -1 charge. So either cross your charges or think about how many of each one you need. You need 1 lead and you need 2 chlorates. So we're going to put that thing in parentheses. And it's 2 chlorates, not 3, excuse me. Let's look at ammonium phosphate. So ammonium is tricky. You might be looking for it on your list of ions that's not there. It's actually a polyatomic ion. Be careful because ammonia is NH3, but ammonium is NH4 with a +1 charge. And phosphate is PO4 -3. So again, we need 3 of those ammonium ions to cancel out that phosphate. And so we need parentheses, right? We need 3 of the NH4 group, and we need 1 of the PO4 group. And that's what's going to give us our neutral compound. Finally, cupric sulfate. Sulfate you can look up on your list is SO4 with a -2 charge. Cupric is copper, but it has a +2 charge. So to get those charges to cancel out, you'd need 1 of each of those. You would end up with CuSO4. You'll notice that sometimes I have my polyatomic ions in parentheses, sometimes I don't. And if you're clever, you'll notice that the times I have a polyatomic ion in parentheses, there's always a number outside of the parentheses. That's when we need parentheses. But you'll notice in the bottom example, CuSO4, and the top example, Na2CO3, there's only 1 polyatomic ion, and therefore we don't require parentheses because we're not trying to put a number outside of it. Okay, let's go the other way. Let's name. The easiest way to name is to think about the anion first. So, hydroxide is OH -1. You can find it on your list. And then the next question you have to ask yourself is, does this cation require a Roman numeral? So remember how we just marked up our periodic table. Calcium is in the first 2 columns. It's actually in the second column. It's always a +2 charge, which means we do not write a Roman numeral, right? We simply write out calcium. What's left after calcium? Well, OH is hydroxide. So we write out calcium hydroxide. And you might say, well, wait a second, that doesn't seem like it's enough information to write that formula. Like, what if I just gave you that name? Don't we need to tell people what these charges are? Like, how are they going to turn that into that? How are they going to know where to put the 2's? But think about if you took this thing backwards. Calcium, you know, is in the second column, so you know it's a +2. Hydroxide is a polyatomic ion where we know its charge is always OH -1. So if you had that arrangement, you would need 2 of the hydroxides to cancel out 1 of the calciums, which is why we have it written like that. So this actually is enough information without the Roman numeral, and that's why we're not allowed to have the Roman numeral. All right, looking at number 2, what do we know about the anion? The anion here is chlorate. What do we know about the cation? The cation is potassium. Does potassium have multiple charges or a single charge? Well, it's always a +1. It's always in the first column. So here we are going to just write out potassium. And potassium chlorate is good like that with no Roman numeral. Looking down at number 3, we have NH4NO3. So split this thing at the cation and anion. NO3 is your anion. NO3 is nitrate. And NH4 is also a polyatomic ion. It always has the same charge, you'll notice. It's always +1. This is ammonium. No Roman numeral required because it's not in that middle box. Looking down number 4, SO4 is sulfate. Looking at our cation. Now we have a problem, right? Fe is iron. But if I gave you that name, you'd look at me and say, well, what the heck? I don't know if you mean iron Roman numeral 2 or iron Roman numeral 3. Why? Because iron can have multiple charges. So if we run into a cation like this that can have multiple charges, we need to identify which charge it is. Now, how are we going to do that? Well, remember the anion is our telltale. It never lies to us. SO4 is always a -2. There are 3 SO4s. So 3 times -2 means the total negative charge in this compound is -6, which means for a neutral compound, the positive side must be +6. But that +6 is spread across 2 of the ions, so each one of those ions must be a +3, which means really this is iron Roman numeral 3 sulfate, or said another way, this is ferric sulfate. And because it has 2 names, we need to write both of those names in. All right, finally, let's look at this one. Again, look at your anion first. PO4 is phosphate, so we can write in phosphate. Au is a transition metal. It can have more than one charge. So we need to figure out its charge. But remember, our anion doesn't lie. PO4 is a -3 charge. Now there's only one of them, so the total negative in this compound is -3. There's only one gold, so that means our gold must be a +3. So that means for our name, we can write out gold, Roman numeral 3, or, because this thing has 2 names, we could also write out auric, phosphate. To represent the second name of AuPO4.